Very good afternoon to all the participants. And it's 2:30 now. And I welcome the third speaker for today's session, Dr. Sunil Yadav. So let me first introduce Dr. Sunil Yadav. Sunil Yadav is going to speak on this physical air security in vehicular to vehicle communication, and probably will start from the basics of physical air security. Then he will build up and go up to this vehicle to vehicle communications and how we can apply the physical air security into that. And tomorrow also he is going to deliver another lecture in the same time, 2:30 to 4:30 tomorrow also, that is reconfigurable intelligent surfaces enabled wireless communication. So Dr. Sunil Yadav is working as an assistant professor in the Department of Electronics and Communication Engineering, Indian Institute of Information and Technology, Allahabad, India. He did his MTech from IIIT Gwalior and did PhD from IIT Indore. He is serving as a faculty in charge of Mobile and Wireless Networking Laboratory at IIIT Allahabad. He has numerous good quality publications in peer-reviewed journals and conferences. His research interest includes physical air security, wireless relaying techniques, operative communication, cognitive relaying networks, intelligent reflecting surfaces, vehicular communication, signal processing, and MIMO system. And anyone can visit his website given on this IIIT website and find out more details about Dr. Sunil. And
so am I audible, sir?
Yes, sir, you are audible.
Okay. Thank you so much, sir. So shall I start?
yes, you can start now.
Okay, thank you, sir. So I'm sharing my slides. Please let me know whether these slides are visible or not.
It's quite visible, Dr. Sunil.
Okay, sir. Let me check once.
Yeah. Okay, it's coming nicely. It's coming nicely.
Yeah. Yes, sir. So shall I start, sir?
Yes, you may start because already 2:32 is there. Yeah.
Okay.
We can start.
So good afternoon, all the members and participants. Today's lecture is basically on the physical air security in V2V communication. So V2V stands for basically the vehicle to vehicle communication here. And this lecture is basically we will deal in this particular lecture for the analysis of how to basically analyze the physical security aspects in the vehicle to vehicle communication. I'll start with the basics of vehicle to vehicle communication. What is the need of this vehicular communication? What are the different strategies, different modeling of this vehicle to vehicle communication? Then we'll build up a framework for the physical security. What is the need of security in the vehicle to vehicle scenarios? And then we'll move for some performance analysis in terms of some performance measures like outage probability. And then we'll try to verify these performance measures with the help of some simulation studies like Mathematica and the MATLAB softwares basically. So that anyone can understand how we can simplify and how we can analyze the performance of such systems. Basically, this is basically one problem here. But we may build up we basically lay the foundation for different performance measures for different systems and the networks basically. So I'll first introduce about the vehicle communication, then the basic problems in the vehicle communication, and what are the different challenges in the vehicle communication, and then we can move further the different channel models, which basically are the very important to analyze before going to implement or deployment of the vehicle communication. Then different security concerns, we will see what are the different security concerns in the vehicular communication, and then quickly we'll move to the physical air aspects, and then we'll try to simplify the performance part and then the validation with the help of the simulation studies. So let me first introduce what is the vehicular communication basically. So as we are in current scenarios and we are talking about the autonomous vehicles, smart cars basically, and which are basically equipped with various onboard sensors, wireless communication modules. Some internet facilities are also being available in the smart cars. Okay, like for example, the Google is planning to launch a new autonomous vehicle. Tesla is also planning to launch new autonomous vehicle. So there is a variety of variety of devices, variety of autonomous vehicles, and the smart cars are going into the for basically are ready for the deployment in the infrastructure. But at the same time, they have put a strong demand for a real-time connectivity, and this connectivity should be available everywhere and anytime. So the basic aim of the vehicular communication here is basically enables the information exchange. That is a communication between the vehicles and roadside units, which definitely is already going into the it is already implemented in the in our wireless communication scenarios. Because let's say there is a vehicle and there is a roadside unit available, so we are still communicating with each other. But idea in the vehicular communication is slightly different. So I'll come to this point. What is the different in this vehicular communication? And the another thing is the communication between vehicle to vehicle basically. So there the people have, the researchers has basically categorized this vehicular communication in four different modes. The first mode is basically the V2V mode, that is vehicle to vehicle mode, and this is one of the challenging mode basically. This imposes a huge challenges while we are going to deploy and going to develop this particular mode in a real time. The another is vehicle to infrastructure, which is already being in use basically, as you have heard about the VNets, the vehicular ad hoc networks. So this is already been in use. The another is vehicle to pedestrian communication. They have separately separated this particular mode because the pedestrian users are very slow mobile users. So they have specifically mentioned this mode as a separate entity. And the rest things are basically included in the vehicular to everything, whether it is connected to the toll gates, gas stations, or maybe your traffic lights, maybe your health infrastructure, and any other entity which is going to be available for communication. So they have categorized basically this in the vehicle to everything communication mode. So these are the typical these four are the typical modes of the vehicular communication. But the main challenge is to model the V2V communication, because the channels in V2V communications are highly dynamic, and the channel is keep on changing with time. So it is very difficult and very challenging to model this V2V scenario basically. So so what type of information we are looking for in the vehicular communication? So let's say if we are looking for from the perspective of our smart cars and the autonomous vehicles are basically equipped with onboard sensors. Okay, so we are looking for information like speed, location, our position, the direction of the vehicle, and the brake status of the vehicle. So these are the few entities which we are actually looking for from the vehicle if they are equipped with various onboard sensors. The another scenario which we are looking for, we want to communicate like as we are communicating from mobile to mobile. So at the same time, we are also looking for a communication between the vehicle to vehicle. So if we are looking for the vehicle to vehicle communication, so our systems, our vehicles basically needs to be equipped with various wireless communication modules. And at the same time, as you know, the Internet of Things is is basically in a huge demand. So the people have also talked about the Internet of Vehicles. So let the vehicles to be equipped with some sort of internet facility, inbuilt internet facility, basically. So these are the basic, some aspects, some of the applications where the vehicular communication can play a role. Now, the different services which the vehicular communication can basically provide, and these are the few which I have mentioned here. One is road safety improvement. Definitely, if the vehicles are communicating with each other, so they may, transmit some of the information. If let's say something is happened, some accident is happened, so they may transmit some of the information directly to the different stations or different central entities. The another one is the traffic efficiency optimization. So they can they can optimize the traffic in a very efficient way if they are being available for the communication. So third one is the infotainment services. Everyone knows currently we want the real-time services everywhere. The music system, musics we require. So this infotainment services can also be provided in the in vehicle communications basically. The fourth one is which I have just talked about, the internet access of vehicles. That is internet of vehicles basically, which is very important. Okay. The fifth one is very important basically, the vehicle platooning. So this vehicle platooning, let's say there's a series of vehicles, available for, or let's say they are traveling from one end to the another end. So the basically the basic management of these vehicles is very much required. And this can only be happen if the vehicles are, let's say talking to each other or communicating to each other, or if they are exchanging some sort of information with each other, then only the vehicle platooning can be maintained. And this vehicle platooning is one of the, may play a major role in case of the military operations, because in case of the military operations, the vehicles are basically in a platoon, and the thousands of vehicles move together. So in that way, this vehicular communication will be definitely a key paradigm in the future, basically. So why basically this vehicular communication is required? So definitely there is a single point here, that is for making our daily experiences on the move safer and more convenient, basically. So this is for our use. So definitely we want to make our life much easier. Okay. So this is the basics of why we require the vehicular communication specifically. Okay. There are several standards basically being proposed by the different agencies, different institutes, okay, related to the vehicular communication. So let me talk about first is, which is very standard and everyone knows about this, that is a VANET, vehicular ad hoc networks. But specifically, if I discuss it, so this is specifically designed for a vehicle to fixed infrastructure, that is a roadside unit, or we can simply say the V2I type of systems, vehicle to fixed infrastructure unit or a mode. Okay, so this basically is already been standardized by the IEEE 802.11p technology, and this was the first emerged technology, that is a dedicated short range communication, DSRC, and this was deployed in the US. The another technology which is or another standard basically for the VANET itself, that is an intelligent transportation system, and this is in a huge demand currently also. This is the ITS G5 standard. So this standard basically was developed by and proposed by the European Telecommunication Standard Institute basically. Okay, so this is the another standard for this particular technology for VANET. The third one is was proposed by the one of the association, that is one of the standardization institute, the Association of Radio Industries and Businesses, that is a T109, and this was basically designed by the Japan. So the another technology which is available for the VANET, or going to be available soon, maybe in the next maybe by the end of this year, or maybe in the next quarter of the next year, that is a 2022. This is 802.11BD. This is the next generation of the 802.11p basically. So this is what we are actually looking for, basically, which we have already available. We are already available with these technologies for the vehicular communication standard. But at the same time, what happens? You know that is a few years back the LTE was proposed, that is a long-term evolution, and this was proposed by the 3GPP, that is a third generation project partnership project, the 3GPP body. So they have also started looking into the V2X scenarios and applications, and they specifically mention, or they separately basically they have separately mentioned the standard that is known as the cellular V2X basically. So now they are also trying to develop some of the strategies, some of the theories, some of the implementable systems for the cellular V2X scenarios. Okay, and this basically for this standard, basically the cellular V2X, there is a one association which is known as the 5G Automotive Association. In a short, we can simply say like the 5GAA, that is a 5G Automotive Association. So they are much interested in the cellular V2X scenarios basically compared to the VANET. Okay, because when there is some sort of challenges or you can say the limitation of the VANET, which may be uh, uh, not yet finalized, but which may be overcome with the help of the cellular V2X scenarios. So they have releases various standard various releases over there. Like in the release 12, they have talked about the device-to-device communication. In release 13, they have talked about the enhanced device-to-device communication. Then they quickly moved to the release 14, and they have been proposed few scenarios, basic services basically for V2X, V2V, and V2X scenarios. Release 15 was related to the EV2X, that is enhanced V2X services. But this release 16 is basically of important use, and which is the people are actually looking for. That is a 5G new radio V2X scenarios. So now they are basically working in release 15 and 16 together. And 16 is because the people are currently talking about the 5G and the beyond 5G scenarios. So they are also trying to deploy various services or trying to design basically various services and applications for for the cellular V2X communication basically. But this specifically, interest basically the main interested body was 5GAA, that is 5G Automotive Association, which basically discussed this particular matter with the 3GPP, and they have released these standards for the deployment basically. Let's see how it will go on, but these just under consideration basically. So the spectrum which is available for these vehicular communication is basically 5.9 gigahertz band, which is widely available, and it is for both VANET and cellular V2X. But right now the people are also talking about for cellular, specifically for the cellular V2X, they are also looking for the 4.8 gigahertz band also. But let's see how they can implement this particular scenario in the 4.8 gigahertz of band. But currently they are testing their all scenarios and applications in the 5.9 gigahertz of band. Okay. Now, what are the different challenges basically which vehicular communication generally has? The first challenge is basically the short-lived vehicle to vehicle and vehicle to infrastructure connections, because we know the vehicles, if they are highly mobile, so they have been the channel between them is highly dynamic, so the connections may be lost anytime. So this is one of the challenge. The another is the channel access delay, definitely. And third is definitely we need to ensure the quality of service, which is definitely which is lacking in the vehicle communication basically. But which I'm basically interested, that is a vehicular channel models. So when we'll talk about the vehicles will be communicating with each other with the in a wireless mode. So there are several scenarios. There are several things which we typically considering in our basic wireless communication as well. That is scattering phenomena, fading phenomena, multipath scenarios. Okay, shadowing, and there is a number of aspects basically, number of things which we need to consider basically. So the major challenge in communication is the vehicular channel modeling. That is appropriate. We need to find out what is the appropriate channel model for the V2V communication. If we want to exchange some information between vehicle to vehicle, so we need to check what is the appropriate channel model for this particular communication, because the conventional channel model will not work definitely. This has been also proved experimentally. Okay, so I'm much interested in the vehicular channel modeling compared to the above three, because you can and there is already several things being proposed at the upper layers like the MAC layer, network layer, to discuss these lack of quality of service guarantee and the channel access delays. So the various algorithms, various things being already proposed for to overcome these challenges. But this vehicular channel modeling, when we'll talk about the vehicular channel modeling, this is specifically for the physical layer part. Okay, so where we'll look into the appropriate channel modeling between the vehicle to vehicle, which is basically a wireless in a nature. So so there are the two the vehicle channels, because they are highly dynamic, so they exhibit. So this is these two are basically well-known phenomena, that is a rapid temporal variability and the inherent non-stationary of the channel statistics. So these two generally being exhibited by the vehicular channel models. So due to which this is very mandatory to establish or it is very mandatory to get the appropriate channel model for the vehicle to vehicle scenarios. So let me talk about the different models which are available in the literature basically. Let's say if we'll talk about the V2I channels, that is vehicle to infrastructure, which the people also use in the VANET, that is a vehicular ad hoc networks. So they are talking about the Rayleigh feeding, which is a widely available and one of the most popular feeding distribution for the wireless communication. Okay, but this is only suitable for the V2I channel models. The another one is the Nakagami feeding, which is more generalized over the Rayleigh feeding, and it is considers the Rayleigh feeding model as a special case also, and there is many more classical feeding distributions are available in the literature. But once we will talk about the V2V channel models, there are the two different modelings which people are talking about. The one is they're talking about the cascade Rayleigh feeding, and the other is the cascade Nakagami feeding. So cascade Rayleigh feeding is very simple. It is there is a number of Rayleigh distributions are in cascade. Like for example, if I'll talk about there is a component H which is Rayleigh distributed. So there is a multiple component like H1 multiplied by H2 multiplied by H3 and so on. So they will basically forming a cascaded scenario. So we'll talk about mathematically in the next slide. But what is available in the literature, that is one is cascaded Rayleigh feeding, and then more generalized distribution is basically the cascaded Nakagami feeding, which is basically appropriate for the people have found this particular these two feeding scenarios experimentally even, that these two feeding scenarios are perfectly fit for the V2V communication, basically vehicle to vehicle channel modeling scenarios. The another way to model the V2V channel is basically the modeling using the first order autoregressive process. This is the another way of analyzing the channels or to model the channels for the vehicle to vehicle scenarios basically. So we'll talk about one by one how to get the cascaded Rayleigh feeding and how to get the modeling using first order autoregressive process basically. So let's first talk about, so here I'm only considering the cascaded Rayleigh feeding rather the cascaded Nakagami, because cascaded Nakagami is a generalization of the Rayleigh feeding. So one can easily calculate later on, but we first understand what is a basic idea behind the cascaded Rayleigh feeding basically. So for this, we just simply to evaluate or to calculate the cascaded or to formalize this cascaded Rayleigh scenario, we must know the basic of the Rayleigh feeding scenario as well as the basic wireless, like the constructive, destructive interference, constructive interference, okay, or like a basic of multipaths, some feeding scenarios like slow feeding, large scale feeding, slow feeding, fast feeding. These basic phenomena we must know. These scattering phenomena we must know. Okay, so these few things if we remember these things, so we can easily derive the cascaded Rayleigh scenario from the Rayleigh scenario itself. So let me first introduce what are the different factors basically, which are basically helpful or which should be considered while we are characterizing our V2V links. And these are the mandatory factors, because we cannot model our V2V as simple as we are modeling our simple cellular scenario, like there is a base station, there is a fixed entity, and there is a slow vehicle mobile device like a pedestrian user or maybe a user which is moving in let's say with via bike or some 50 kilometer speed of basically via car having a speed of 50 kilometer per hour, like this. So V2V basically is a slightly different structure, and these are the key factors which needs to be properly investigated and properly considered by designing the modeling of Rayleigh modeling for V2V channels basically. So the first one is a type of environment. The urban, we need to check basically our environment is an urban scenario, is a suburban urban environment, is a rural environment, there is expressways areas or simple city areas basically. So speeds basically. So we need to check, and in each and every case, it is slightly different. Okay, or we may model, or we can say by by considering or by assuming some sort of situation, we can make or we can basically reach to the conclusion that this particular type of fading distribution will be perfectly fit for the cascaded for the vehicular to vehicular communication basically. The another important aspect is the antenna elevation, which is very important, because what is happening, if you see the cellular scenario, in the cellular scenario, your base station is having a having a height of antenna, let's say 30 meter, 40 meters, for example, and the let's say there is a user having a mobile device, its height is like a 6 feet or something like this, or 5 feet. An ideal average height is 5.5 feet, for example, if it is carrying some sort of mobile with this. So the antenna elevation at the transmitter side and the receiver side is very important to investigate before characterizing the models for the channel models for the V2V links basically. The another is the separation between transmitter and receiver. This is again a very important aspect, because the vehicles are moving, let's say if we want to communicate two bullet trains, for example, and they are crossing to each other in opposite directions, and their speeds are like maybe 500 kilometers per hour. So it is, we need to we need to consider this scenario. Separation is basically slightly different aspect here. Let's say one vehicle is moving, let's say 50 kilometer per hour in a one lane, and in the fourth lane, another vehicle is moving, let's say some 80 kilometer per hour, 80 kilometer of per hour of speed. So we need to check the separation between these two, and accordingly we need to model, and we need to consider these conditions while we are designing our models. This fourth is definitely needs to be considered, the power of scatterers, waves, and power of dominant component, which is a basic component. The another is a single and multiple scattering phenomena. This is very important, because what is happening basically when we'll talk about the Rayleigh fading, classical Rayleigh fading, simple, as we are considering our basic cellular scenarios, so we generally assume it is a Rayleigh scenario, okay, Rayleigh fading distribution. So, and the Rayleigh fading distribution is generally characterized by a single scattering phenomena. So, but there may be the situation when there is a multiple scattering phenomena. There is a multiple scatterers are available at the transmitter side, and the multiple scatterers are available at the receiver side. So we need to consider this multiple scattering phenomena as well, and definitely the mobility, because the vehicles are moving with some sort of speed. So let's say if we are considering these all aspects or if we are considering all the factors while characterizing the links, while characterizing the V2V models, so we can simply express our HT, that is a transfer function, as a linear combination of some components like Rayleigh, double Rayleigh, and triple Rayleigh, etc. There may be number of, or maybe the cascaded Rayleigh and distributed amplitudes basically. So how to express this equation? So this is the equation. So here the channel transfer gain base or the channel transfer function basically written as the W1 H1T. This H1T is specifically known as the Rayleigh distribution. So if we'll talk about the classical Rayleigh fading distribution, so we'll only have the one component, that is a W1 into H1T. That's it, nothing more than that. But when we'll talk about the some another components like H2 multiplied by H3T, and in this case like H4 multiplied by H5T multiplied by H6 of T, so they've been characterized by the different distributions like double Rayleigh distribution, triple Rayleigh distribution, where this H2T, if you see this H2T, it is specifically as known as the Rayleigh distribution. This H3T is separately known as the Rayleigh distribution. So when we are multiplying these two or cascading these two, these known as the double Rayleigh distribution. So the problem is not the problem. So first we need to characterize. So first we need to express our transfer function. And this particular transfer function which is mentioned here, it is basically or according to the scattering phenomena, this phenomena which I mentioned here, the multiple scattering phenomena. So if there is a single scattering phenomena, so you will undergo the Rayleigh fading distribution. If there is a multiple scattering phenomena, but at the same time you have to consider these conditions also. So you may undergo to the double Rayleigh distribution, triple Rayleigh distribution, and finally the cascaded Rayleigh distribution. So this is the generalized equation, although, but the problem is still the people are facing one problem. We still don't know which component, whether the second component or the first component. When I'm saying the first component, my meaning is H1T I'm talking about, and when I'm saying the second component, that is a H2T and H3T I'm talking about, the combination of these two basically, and the third component is this, and so on. So still the people are experimented this thing. So which component is dominating, basically which component is dominating, whether the first component is dominating. So if it is first component is dominating with some experiments, so definitely it will go under the Rayleigh distribution. If the second component dominating, then the scenario will go under the double Rayleigh distribution, and accordingly the triple Rayleigh distribution, and so on. So this is another challenge, basically how to get the accurate information about the dominating component. But by the several experiments, it has been found that in most of the cases, when we will talk about the V2V communication, our double Rayleigh distribution will be the best suited channel model for the vehicular to vehicular links, basically. So then, but how to calculate, basically we mentioned here it is a double Rayleigh distribution, but what exactly within this double Rayleigh distribution is. So but so here a few consideration we are assuming, like nodes are in motion and they are having the low elevation antenna. For example, one antenna is available at the or equipped at the car, one of the car dashboard. Another is equipped with the another car dashboard, basically. So they are having the low elevation antennas, and at the same time this third one is very important, which needs to be considered, that the scatters basically which will generated near the transmitter and the receiver vehicles are basically the randomly and isotropically distributed with different radius. Okay, with different radius. So this also needs to be considered while we are analyzing the models, basically. So this is the typical equation. If here I'm just in equation 2, I'm just simply talking about the double Rayleigh scenario. If it is a triple Rayleigh scenario, there will be the three sums: this 1, 2, and the another sum. If I'll talk the single Rayleigh scenario, that is only Rayleigh distribution. So one sum will be removed from here, and accordingly the equation can be adjusted. So there are the different symbols here. So let me introduce these symbols. The N and M are basically the scatterers which are generated near the transmitter and the receiver vehicles. This FT and FR denote the respective maximum Doppler shifts, which is due to the speed of mobility or motion of the transmitter and receiver, basically. And the theta N and theta M, and these are the random angle of departure and the angle of arrival, respectively, for the transmitter and the receiver. And this phi NM is the joint phase shift, basically. So this particular equation is nothing but the generalization of the simple Rayleigh distribution equation, which we can easily calculate it with the help of the by modeling a basic system like a transmitter, and there is a receiver, there is some scatterers in between. Okay, and then we can basically the multipath fitting scenario. So this is the generalized equation. So but the problem here is the motion of the transmitter and the receiver, which are basically involved in terms of the Doppler shifts to determine how fast the fading channel will be. So what is happening here? You will see the problem here in this particular. So let me come to this point later on. This point. Let me first introduce few more things. So we need to consider. So we need to consider the channel between the moving vehicles to be quasi-stationary for a short duration. Means for a one fading block time, I'm assuming my channel is stationary. Okay, and then The another assumption, the distance between the nodes, that is the separation basically, that between the nodes is greater than the scattering radii. So the equation is something like this here. If let me write down here, if you can see, I think. So when I talk about this particular part, so my aim is basically the distance. The distance is basically the very greater than the maximum of, let me correct it. It is very greater than the maximum of n comma. This is the meaning. The distance or the separation between the nodes, these two vehicular nodes, is very greater than the scattering radii basically. So which are number, or here it is a, so I have mentioned here from n or m, but if you go to the literature, you may found this n or m basically related to the Rn and the R of m. That is a the radius of the n number of scatterers formed and the radius of the m number of scatterer forms basically. So this is the condition basically. And the first condition which I have mentioned here, that is the channel between the moving vehicles to be quasi-stationary for a short duration basically. So we need to, we are assuming that our channel is constant for a certain duration. That is, you can apply the funda of the coherence time basically. Okay. So by considering this, if we consider these two conditions, we can simply express our phase shift, that is a joint phase shift, is equal to the theta n plus theta m. And if you invoke this theta plus theta m in equation number 2 and simplify it, you will observe the double sum basically in equation number 2 can be expressed as a product of the two single sums. And then it simply leads to the double Rayleigh phenomena. Because if you see this equation number 2, you cannot express separately because this is a joint phenomena. Phi n m, it is a joint shift. So once these conditions are true, or these conditions are assumed, this particular equation can be simply written as, or this phase shift can be written as theta n plus theta m, and accordingly this double sum in these two can be expressed as the product of the two single sum. And when I'm saying the product of the two single sum, which indicates that one sum consisting of some quantities is known as basically the Rayleigh distribution, and then accordingly the second, and it is known as the double Rayleigh fading distribution. So, but now here if you observe, so I'll come to the distributions. What are the different how we will actually express the distribution of double Rayleigh fading. Okay, the probability density function and the cumulative distribution function of the double Rayleigh fading channel. So here what is happening, we have, if you see this this expression, this particular expression, equation number 2, I'm not considering the velocity factor, the mobility factor. Okay, and at the same time what I'm assuming, the motions, basically the speed of mobility, or you can say the velocity basically of the transmitter and receiver are basically involved in form of the Doppler shift, FT and NFR simply, and they are actually defining, or they are actually determining the how fast the fading channel will be. So I'm not specifically characterizing, I'm not specifically mention what is the relation between the FT and the velocity further, okay, or any other quantity. I'm just simply assuming in this particular case, the FT and NFR are the simple Doppler shifts which are helping us to determine how fast the fading channel will be, that's it. And that's why the double Rayleigh fading distribution occurs after considering these conditions basically. And this has been if you can if you are interested, you can go to the one of the paper that was written by the J.B. Anderson, okay, over the multiple scattering phenomena for mobile to mobile communication. You will find the double Rayleigh fading is experimentally proven for the vehicle to vehicle scenarios, okay. And this been already applicable for, this can easily be applicable for various practical scenario. One is very popularly known as the rush hour traffic scenario. So this cascaded scenario is applicable for the vehicular communication when we are in the rush hour traffic. another scenario is basically, just assume that one mobile terminal is located indoors, okay, in a low-rise building. For example, the height of the building is 10 meter, and the another mobile terminal is placed outdoor at the roadside, basically. So in this particular situation also, it is proven that the cascaded fading envelope distributions are the appropriate model for the V2V scenarios. And remember this, the users are mobile in both the cases. Like if you are in the if you are located indoors in the low-rise building, it's still you are a moving device, basically. You are moving with your mobile phone. Let us assume like this. And the another mobile phone which is outdoor, so you are still moving. So the cascaded fading is found appropriate here. The another is when the mobile nodes are located relatively dense scattering phenomena, like let's say vegetation, or the another example is a traffic scenarios. As I mentioned, the first case, the rush hour traffic, the traffic is very dense, basically. So in such scenarios also, the channel between the vehicle to vehicle is also be good fit for the cascaded fading distributions, because this is one of the important aspect we generally ignore while we are deploying or designing our systems. Let's say if the people are talking about the VNet, the vehicular ad hoc networks, and they are designing something, so they are not considering the appropriate channel modeling. Okay, they are just simply assuming few things. Okay, let's say consider this as a scenario. There is a one scattering phenomena introduced into the some sort of modeling. Okay, we cannot do like this. So because our communication will be at the physical layer, so the channel model at the physical layer should be appropriate. Okay, so and we found here, and it has been already available in the literature also, the cascaded distributions are the appropriate models for the vehicular to vehicular scenario, basically. Now the another model, another way of modeling the V2V channels, basically, it is using the first order autoregressive process. So let us consider a few things here. So as we have seen in the previous case, we have just simply ignored the coherence scenario. So let's discuss it here. So when the symbol period of the detected signal is larger than the coherence time. In the previous case, it was a lesser than the coherence time. That was fixed for a certain duration, one fading block time. Okay, there's a quasi-stationary that we have assumed. But here it is greater than the coherence time. So which means the system fading links can be characterized as a time selective scenario. And then accordingly, the equation for the channel between two vehicles, let's say I and J, should be written as like this: rho ij h of ij t minus 1 plus this root times of this equation. So this particular equation will be known as the first order autoregressive model, basically autoregressive process. And here the different assumptions in this particular equations are basically the t and t minus 1 basically denote the different two adjacent signal period positions. This random process EIJT, that is basically an error here, is again a varying component, and the varying component with density simply the complex normal with zero mean and some omega variance. Now this rho is basically known as the correlation factor, which is correlating between I vehicle and the jth vehicle, or you can say between two vehicles, basically. And now you can observe this rho is basically a function of v, velocity here, Vij. So I mentioned here the Vij is the relative speed or the velocity between the nodes I and J, where R is denote the transmitted symbol rate, Fc is the carrier frequency, C is the speed of light, and J naught is simply the 0th order Bessel function of the first kind. But the main aim here is your correlation coefficient, basically, or the parameter, is a function of velocity. Okay, which if you can see here in the previous case, if I'll go to this case, we have ignored this velocity factor. Why we have ignored? One thing is the Ft and Fr is basically denoting the maximum Doppler shift, and they are actually determining the how fast the channel will be, and they are actually determining the velocity of the scenario. And at the same time, I have also considered the quasi-stationary channel. So in that case, I'm assuming my channel for a certain duration is constant. So the relative velocity aspects I'm just ignoring. The velocity aspects I'm ignoring here, but it is being introduced in terms of the FT and NFR. And accordingly, if you calculate, if you simplify this equation number 2 further, you will get to know the double Rayleigh fitting distribution. We will see what type of distribution mathematically you will obtain, but this you will get. But here, the another model which is basically following the autoregressive process method, considering the correlation between the two vehicles is a function of the velocity directly. So accordingly, you will observe if you are increasing the velocity, the correlation factor will be decreasing. If you are increasing decreasing the velocity, the correlation factor will be increasing. That is an inversely proportional relation. So you can also observe here, if I'll write here, you can calculate from this equation basically that if velocity is 0, that is you will get rho is equal to 1, and if velocity is going to be infinity, high, so this is going to be 0, like this. So you may get this scenario. So rho is equal to 1 is ideal situation. So if you invoke the rho is equal to 1 here, this quantity will be 0, this quantity will be 1, and your HIT basically is equal to the h of t minus 1. That's it. That is both are equal. So it is a stationary scenario then. So this basically leads to the stationary or a fixed scenario, or static, basically static scenario. This is basically the static scenario. So you can calculate you can calculate few observations from this relation, and this relation will help you out to introduce basically the velocity factor, the distance separation between these two, and various other factors if you model this particular. If you are interested, we just now published one of the paper in IEEE Open Journal of Vehicular Technology. It is available online, so you can go through this particular paper where we have we have analyzed the system performance with the help of the first order autoregressive process modeling, and we have analyzed several cases of interest under this modeling basically. Here simply the HT denotes the frequency flat time selective complex Gaussian fitting coefficient, and this is the important aspect here. It is just simply the Rayleigh envelope. If you see here, it is here I'm not considering that is a double Rayleigh. That is a different modeling under the consideration of few assumptions basically. Here it is simply with the Rayleigh distribution, means this HIT is a Rayleigh distributed and this HIJT is a Rayleigh distribution. That's it, nothing more than that. The main factor is here is rho ij, which will play a very important role while you are simplifying the performance of the systems basically. So this is how we need to model. This is how to or different type of models which are available for vehicle to vehicle scenarios. Okay, and these models needs to be considered while you are analyzing the system performance basically. You cannot ignore the one of the basic fundamental of the channels. So that needs to be considered. Now both the models which I have mentioned here, the cascaded scenarios and the autoregressive process, being widely adopted and widely used under different scenarios. Okay, the one of the literature suggested that if you go into the if you are having a speed of, let's say, some 100 kilometers per hour, let's say in India the typical speed is 120 kilometer per hour. Okay, in a cities you have a speed of, let's say, 40 kilometer per hour, 30 kilometer per hour. Okay, so in that scenarios, the that is specifically mentioned the if you are talking about the greater than 50 kilometer per hour, but we'll, let's say, consider the 30 kilometer as a benchmark speed. So this autoregressive process model is much appropriate. Okay, but if you are as a slow moving users, let's say as we let's say moving with a for example 10 kilometer per hour or the some 20 kilometer per hour for example, so the double Rayleigh fitting distribution is much more appropriate compared to the autoregressive process. So these two are the different according to the different applications, and these all are experimentally proven as well. Okay, so at the same time, once we will talk about the V2V communication, so because the communication is happening wirelessly, so there is a few security concerns as well in the vehicular communication. But here, definitely, there is a number of security concerns for wireless scenarios, like there is a DOS attacks and then multiple attacks basically available. But I'm just interested in the physical error attacks basically. because we are actually talking about the physical layer aspects here. So we need to secure our systems basically from the malicious attacks in order to improve the system performance, user privacy, and the data privacy. Okay, so there are the three major attacks basically which generally occurs at the physical layer. One is jamming, another is spoofing, and the eavesdropping. Okay, jamming, you know that some of the user or maybe the entity may transmit some of the signal to jam the communication between the two devices or the two vehicles. For example, spoofing is something like this. For example, it look like that you are a legitimated one, but actually you are the some intruder. Okay, so you are stealing the information, and one of the one of the dangerous attack basically that is known as the eavesdropping attack. Okay, because even the eavesdropping attack is basically further can be divided into two parts, that is active eavesdroppers and the passive eavesdroppers. But the passive eavesdroppers is one of the dangerous one, because you don't know where the eavesdropper is basically. Because if it is an active eavesdropper, it is definitely it is transmitting some sort of signals or some sort of the information. So that information can be extracted by the transmitter, and then accordingly it can design their own policies and the strategies to jam the particular eavesdropper if it is active in a nature. But if it is passive in a nature, then it is very difficult to obtain the information of that eavesdropper. Okay, and this is one of the challenging tasks. How to model our systems, how to analyze the performance of the systems basically when the eavesdropper is basically passive in nature. So what are the impact basically of these three attacks? They can steal the information, steal the vehicle identification and authentication, definitely, because currently we are talking about for example, let's take an example. If your vehicle is passing through a toll gates, you may get your information may be steal. Okay, your information can be intercepted. Okay, the identification, authentication can be intercepted. Okay. Another thing is manipulating communication between vehicles. Definitely, these can manipulate the communication between vehicle, and this one of the major concern, as this manipulation is a serious concern if you are looking the military services. When in the first slide which I have talked about, like the vehicle platooning. So that's why the vehicle platooning is very important. If you see. But at the same time, there is a concerns. There is a problem of the security related things in the vehicle platooning as well. Okay, because someone may definitely manipulate the communication or the information exchange between the vehicles. So this we needs to this we need to consider, and we need to adopt it while we are designing our models basically. So there is different communication. There is nothing, the communication security is not a new approach. Basically, there are several strategies and schemes are available. Several techniques are available in the literature. If you'll go from the, if you'll discuss the cryptography methods, basically, they are basically what are the disadvantage of cryptography methods? Basically, definitely they are of huge. They are in huge demand. They are widely applicable, widely implemented as well. But some of the some of the problems with the cryptography methods are basically they are the key based approaches. You need to have some private key, public key scenarios, and they generally applied at the higher network layers, not specifically for the physical layer. And if you see the with the advancement of the new encryption standards and the data encryption standard algorithms, they require a huge computational processing. They require a huge computational resources as well. So these are few disadvantages basically. Okay, but if you see the physical layer methods, it is very simple. They just simply exploit the physical layer properties of the wireless communication, such as interference, fading, path loss, shadowing, etc. That's it. Nothing more than that. And we know how to model the different properties of the physical layer. We know how to deal with the interference. We know how to deal with the feeding scenarios. We know how to deal with the path loss and the shadowing as well. So they are just simply exploiting the physical layer aspects of the wireless communication. Okay, what are the advantage in physical layer? There is a no assumption of adversary computational power. Means if I talk about there is a passive eavesdropper or let's say eavesdropper, so I'm not assuming, I'm not putting any constraint on the computational power of the eavesdropper. It may have the infinite computational power, doesn't matter. My just simply aim to extract or just to exploit the characteristics between the legitimated user and the eavesdropper. That's it. Okay, it may have the infinite computational power. Okay, I don't care. That's it. Then there is a no assumption on the eavesdropper available information. It may have number of information available, doesn't matter. Okay, another one is implementable using signal processing, communication and coding techniques. There is a widely available techniques by which, and the people are also still working with the in order to deploy the physical security aspects, basically with the help of the signal processing schemes, various communication models and various coding techniques. Here the people are also talked about the directional antennas also. If the antennas are highly directional, so the whole information will go into the legitimate direction, and the side lobe consists of a very small information will be fetched by the eavesdropper. So this is another aspect. The people are talking about the coding techniques, like the CDMA is one of the safest. You people know that the CDMA is one of the safe technique, but it has their own disadvantages. But the people are also integrating the CDMA in more more advanced way. So these are the few aspects where the physical layer security can found. So we are not claiming that the physical security is an alternative of the cryptography approach. No, it's just you can assume it's a complement basically of the cryptography schemes. Okay, rather say like it's an alternative, it's a complement of the cryptography approach. Okay, because here we are and some of the researchers has proved it or they are basically claimed it that this physical, if your data is secure at the physical layer, there is no need to apply the security schemes or the security techniques at the upper layer if you are able to secure your data at the physical layer itself. So but let's see how it will go further and it going to be implemented. That is another area of interest, but some other researcher has claimed it. Okay, so quickly I'll give you the overview of the how the physical security generally works. So let us consider the information theoretic approach here. There are several approaches available in the literature, but let me consider only one approach here. So let us assume the L is basically some A wants to communicate with B, and this B is basically a legitimated user. But this eavesdropper is basically available in the network, which is going to intercept the information, going to intercept this particular information. So this is a typical simple model between the transmitter and the receiver, for example. So I have mentioned also here, this is the legitimated channel, and the channel between the LS and the Eve, it is known as the wiretap channel. So what is happening here? There is some message W. It is being transmitted by the LS. So what LS will do? So LS, let's say transmitter. So transmitter will generate a XN, that is a code word of N length, and it will be received by the Bob in terms of the YN. So the code word of YN. Definitely there are some errors. Let's say if a code word of length 100 is transmitted, so you will receive only 90 length code word of length 90, for example, like a number of bits you can assume it. Okay, but at the same time, the eavesdropper is also fetching the information, also intercepting the information with the help of this code word of length ZN, like this. So how to characterize then? How to characterize? So the information theory, as you know that the information theory is typically based on the channel capacity, and you know what is the channel capacity? The maximization of the information between the or information of the channel basically. So here we have just assumed like the CM is basically I'm denoting the capacity of the legitimated channel, and the CE I'm assuming the capacity of the wire tape channel. So this particular channel having a capacity of CM, and this is basically having a capacity of the CE. So this is from the information theoretic perspective basically. There may be another perspective, as I earlier discussed, that is a beam forming approach. That is you need to design a highly directional antenna which is only dedicatedly available for the legitimate user rather than the eavesdropper. So the small, the side lobes of that directional antenna are are so much small, so they are just carrying a very small information, which is you can assume it to be negligible. But that is another designing the directional antenna for number of users at the same time, it is again a difficult task, or otherwise you need to design an array of antennas which specifically dedicatedly for having a directional beam for each user, so which is definitely a difficult task, and as a complex task, as well as the cost involved, basically the very costly affair basically. Okay, so that's why we are interested here in an information theoretic sense basically. So let us first discuss this information theoretic approach so that we can get the idea what is happening while we are analyzing such systems. So let us assume if the quality, first condition, if the quality of the wire tape channel is worse than the legitimate channel. So here we are just planning with the channel qualities basically. Let us assume this channel quality between A and B is much better than the channel quality between between the E and E, basically the Alice and Eve. If this is happening, then the Bob can simply decode the simply receive or decode the signal with the negligible error. If this is happening, because the channel quality of the main link or the legitimate link is much better than compared to the wire tape channel. Okay, this is the first condition, which is definitely a favorable condition for us. And in this case, the eavesdropper cannot extract any information. That's why this information of this masses, sorry, I have mentioned M here. It is basically the W. It should be W here because I am transmitting W as a message. So this I W for length Zn should be equal to 0. So this the information is basically equal to 0. So which basically indicating that there is no information, no message signal being received by the eavesdropper. And then finally you can conclude that it's a perfect secrecy. That is your system is a perfect. You have achieved the perfect security in the system. But at the same time, if you see the quality of the wire tape channel is better than the legitimate channel. In some case, if it has happened, the strength of this particular channel is much better than the strength of this channel. This may happen. How it may happen? Eavesdropper is very nearby the Alice. This is one of the scenario. It is very closer to A. Then the channel strength of the eavesdropper is much better than the, and if the B is very far away, for example. Okay, so then in that case, the strength of the wire tape channel is much better than the strength of the legitimate channel. So in that case, you will get the perfect eavesdropping. Means all the information will be fetched, all the information will be intercepted by the eavesdropper, and you won't get any information at the receiver side or at your legitimated user. Basically, the whole information will be received by the eavesdropper. So that's why we need to, while we are characterizing our vehicular to vehicular communication, this physical layer security aspect at the same time is very important to consider. Rather, and when we are talking about the privacy, let's say vehicular platooning, when we'll talk about vehicle platooning for the military purposes, so the security is of more concern basically. So we need to integrate our physical layer security aspects in a V2V communication to improve the system performance and the system security as well. So finally, if someone looks into this whole scenario and wants to analyze the system performance, So the system performance can be analyzed, or you can say the physical security performance basically can be analyzed with the help of this particular formula. So now the capacity, which is basically I have assumed here CM and CE for the respective links, is now modified, known as the secrecy capacity, which is the maximum of CM minus CE, comma 0. Means if CM is greater than CE, definitely this is our favorable case, the case number 1, which you have mentioned here, and we'll get the perfect secrecy. But at the same time, if the CE is greater than CM, so definitely the perfect eavesdropping means the secrecy capacity will be 0. So we need to consider this as in case of the in case of the statistics of the or while we are analyzing the system, because you won't get the negative, you won't have the negative data here. Okay, so this is the maximum of this. Either you will get the CM minus CE or 0. That's it. So CM minus CE case basically when CM is greater than CE. Otherwise, you will get 0 to it. So this is the key metric basically. This is the key metric to evaluate the system performance of the vehicular to vehicular scenarios. So here we have seen 2 different approaches, and this is not basically the physical layer is not physical layer security is not specifically, which I have discussed here, not specifically for the vehicular to vehicular communication. You can apply anywhere in the wireless communication, but here the idea is because vehicle to vehicle communications are more dynamic and they are cooperating to each other basically. So due to the open wireless medium, due to the open nature of these communication scenario, due to the cooperativeness between the vehicles, due to the nodes mobility, the security concerns are basically more prominent. Okay, so we need to address the security concerns, and we know that the physical layer security is one of the potential candidate to deal with. So we can integrate the physical layer security in the vehicular to vehicular communication. Okay, so this is the basics of vehicular to vehicular communication. So is PPT is not visible? Someone has messaged.
It's visible, sir.
It's visible, I think.
Yes, sir.
Okay. Okay. So. Okay. So we can simply have the physical. So we should integrate the physical layer in the vehicular to vehicular communication basically, and then we need to analyze the system performance. So the next. So this is all about the basics of vehicular to vehicle communication and the physical layer security. Now next I'm going to take a simple scenario or a simple case study, and accordingly we'll try to evaluate the performance of the system so that you people know how to calculate the how to analyze the system performance in terms of the different measures, performance measures basically. Okay, and then we will try to validate these expressions with the help of the simulation studies basically. Okay, so now I'll use my digital pad so that I can interact more with you people by writing the all derivations step by step. So here I'm just considering one scenario that is a simple source, that is, let's say transmitter, one vehicle, and this vehicle wants to communicate with this particular vehicle, that is a D. This is the source, this is the destination. Source wants to communicate with destination in the presence of the eavesdropper. This is the scenario. This is a simple case. Few assumptions we have considered. The channel HM, the channel between the source and destination, let us assume to be HM, and the source and eavesdropper, let's assume to be HE here. So this we have assumed. Now at the same time, I'm considering the HM and HE. I'm considering HM and HE are the double Rayleigh distributed. So I'm considering the case of double Rayleigh feeding here. I'm considering the case of the double Rayleigh feeding, rather considering the case of first order autoregressive process basically. So that you can also simplify. Okay. So let us assume the HM and HE are double Rayleigh distributed. So the first thing is how to what is the meaning of double Rayleigh here? So when I'm saying HM, so HM is basically the multiplication or the product of two components. Let us say assume HM1, HM2, and HE is basically HE1 and HE2. So this is the multiplication or you can say the product of two components where HM1 and HM2 both are independent. You can assume they are independent and identically distributed, and you can also assume they are independent and non-identically distributed. When I'm saying independent, which means HM1 is independent to HM2 and they are identically distributed, means they have same mean and same variance. Or if I'm considering they are non-identical, you can simply assume it they are having separate variances basically. Okay, so let us consider here the HM1, HM2, HE1, HE2, all are basically because it's a double Rayleigh process, so individual component is a Rayleigh component. So we can write like this. And I'm assuming they are non-identically distributed. That is, all are having their own variances. So this Cn is basically complex normal behavior, basically the process. As we know, that is a Gaussian process. Okay. So this, once we have defined these or we model our channels basically in terms of the or we model our channel like zero mean and omega m1 variance, omega m2 variance, omega e1 variance, omega e2 variance corresponding to their different channels basically. So we can simply write like this. So okay, let me come to this particular point again. So we have defined these first, and then we know that my channel HM is basically a product of these two quantities, which indicates that it is a double distribution, a double Rayleigh distribution whose PDF and CDF needs to be expressed. So let me first give you the PDF. So I'm using this HI here. I means basically belongs to both M and E, because accordingly you can simplify it. This is I1. I'm writing it in a generalized way. This is I2. This is K naught X divided by root of omega I1 omega I2. You can write like this. So this is the PDF. This is the probability density function of double Rayleigh feeding channel. Similarly, you can express the CDF, that is a cumulative distribution function, that is 1 minus x of root of omega I comma 1 omega I comma 2 and k1 x divided by root of omega I1 and omega I2. This. Now if you see here, this k basically, so let me define this. This is equation number 1 and equation number 2. If you see here, this k naught basically and k1, these are the Bessel functions. Bessel function, or also known as the modified Bessel functions of zero order or the first order basically. Okay, so definitely if you see, and let me express here this individual component. If you see the Rayleigh feeding channel individually, if I'll write the PDF of this, you will write like this. That's it. Or better, you should write like this. This is the PDF. That's it. Because here I'm just talking about the Rayleigh distribution. So if you see the distribution of HM1 only, it will look like this. And for each component, HM2 itself will look like this. HE1 separately look like this. The only thing you need to change instead of omega M1, you have to use the omega E1. That's it. and similarly like this. But here, once these two been multiplied and you calculated the probability density function and the cumulative density distribution function, you obtained that this is the probability density and the cumulative distribution functions respectively for double Rayleigh scenarios of HM and HE. And definitely this particular scenario is more complex compared to this, because this consider a Bessel's function, which is definitely a special function, whereas if you see the individual Rayleigh scenario, it is simply consider an exponential function, which is very elementary function, which is widely used and widely applicable also. So that's why while we are dealing with the systems and different scenarios, let's talk about a simple cellular scenario where there is a base station, is a fixed infrastructure, and there is a mobile vehicle. So we generally assume the channel between these two entities is modeled as the Rayleigh feeding distribution. But here we have seen that once we are having the vehicle to vehicle scenarios, under the several assumptions, under the different conditions like multiple scattering phenomena, low elevation antennas, the scatters of presented near the source and the destination are having the different scattering radii in different orders. Okay, so accordingly we need to consider our channel models. Okay, and what we have obtained here, this channel model is slightly not slightly, it is a totally different compared to the normal Rayleigh feeding distribution. It's nowhere consist of the exponential as elementary function. It is some new functions like some Bessel function of some this is basically known as a modified Bessel function of second kind and zero order. If it is k0, it is zero order. If it is 1, it is first order. Okay, so this is a modified, which is definitely a special function. So under this consideration, we need to simplify our expression. Now, let me first express the equations what you will receive. Now let's see what you will receive at the receiver side. This is our simple example. This is D, this is HM, and this is E, and this is H. Now, one thing is also very important to consider. I'm assuming this eavesdropper is passive in a nature. This I'm also assuming. I'm not assuming the active scenario. I'm assuming the passive scenario of the eavesdropper, which is one of the tedious consideration basically in this system. Because if the eavesdropper is passive, it is a non-cooperative and will not transmit or will not feedback its information to the source. If it is not revealing any information, if it is not revealing its location, position, whatever, so it is very difficult to predict, or it is very difficult to get the information to estimate basically the eavesdropper channel. But there's a few strategy which people actually considers or consider while analyzing. The first assumption basically they're assuming, because we know that the eavesdropper is non-cooperative in a nature and not interested to feedback its instantaneous information, basically the instantaneous channel state information to the legitimate node, definitely. So what we are considering only the statistical knowledge of the eavesdropper, basically of the passive eavesdropper, by assuming that the channel, or there are two assumptions here. One is at some point of time eavesdropper was the part of the network, and if it was the part of the network, its information, its location, its position, or any information is available to the code available in the code book of the source, basically. So this is one assumption. Another assumption is if the eavesdropper CSI does not change under the assumption of the quasi-stationary. So definitely in this particular case, because the channel is a double Rayleigh distributed, so we are assuming the channel to be quasi-stationary. So we can easily assume the eavesdropper is a passive nature, or by assuming the passiveness of the eavesdropper, we can simply assume like this: the channel between source vehicle and the eavesdropper vehicles to be a double Rayleigh distributed. So this is another assumption. A very there is another case where the people are actually interested to obtain the information from the RF side basically. So what they have been suggested, each and every device consists of some RF front end basically, and definitely the RF front end has a leakage problem. It is widely accepted basically. There is a very small frequency being leakaged from the RF front end always. So if we can detect this frequency leakage, okay, so we can identify where the passive eavesdropper is. However, this detection of this small frequency is very difficult, but if we can detect this frequency, we can have the we can get the information about the eavesdropper, or we can estimate this information easily, okay, or instantaneously basically. So the people have also proved this particular scenario. There have been proposed few detection algorithms as well, and few algorithms you already know, like maximum likelihood, map estimation, and some optimal detector also available. So by the help of these available detectors, they have tried to get the information from the leakaged frequency of the RF front end of the eavesdropper basically. So these are the few considerations by which we can model the passive scenario of the eavesdropper. Okay, so if you see the simple information here, so let us assume the source is transmitting some information, let's say XS with the power PS to the destination via the channel HM, and at the same time there is a passive eavesdropper which is just sit silent, which is basically available for intercepting the information and not revealing its own information. So we need to check how to simplify this particular scenario. So first we need to check what are the different signals you will receive at the receiver side, and at the same time you are also assuming here it's a single antenna scenario. I'm not considering the multiple antenna scenario. If it is a multiple antenna scenario, then you have the situation of the order statistics. Okay. So let us consider the signal received at the receiver YD, and it's a very standard and typical equation between source and or you can say the transmitter and the receiver. So this I'm directly writing here. So where here it is PS is the transmitted power, HM is the channel between source and destination, XS is the basically the transmitted symbol from the source, and ND is the AWGN, additive white Gaussian noise. And this we can also model. This is nothing but the complex normal with zero mean, and let us assume some N naught as the variance. Similarly, we can get the, so this is at D basically. If we'll talk about the at eavesdropper side, so we'll get the information like this: HE XS plus NE. And also we are assuming this is the AWGN having complex normal with zero mean and N naught variance. That's it. So these two equations we have obtained. So this should always be the first step basically of any performance evaluation. This is the first step, or let's just assume the step number 1. In the second step, what we need to do, in the second step, we must understand what is the requirement, what is the performance requirement. So the how, or what is the basically the how, or you can say like this: how to evaluate the performance of the system. So the first metric to evaluate the performance is known as the instantaneous SNR. Instantaneous SNR means signal to noise ratio. Instantaneous signal to noise ratio. Why I'm giving the instantaneous here? Because my channel are instantaneous in nature basically. HM and HR are both are the instantaneous channels. So I can simply calculate from this that the at D, let us assume I'm assuming some symbol lambda D. So how to write the SNR? This is the signal term and this is the noise term. So signal power, when I'm saying the signal power to noise power, which means this needs to be squared basically. So PS HM of square divided by noise power, that is N naught simply. And if it at E, I can write like this: PS by N naught HE of square, like this. So let us the SNRs. So this is the first metric, the also known as the first performance matrix, basically performance measures, which is known as the SNR basically. Okay, now if you see here, then the third step should be like, we need to define the capacities basically, or the instantaneous capacity basically, instantaneous capacity. So if you define the instantaneous capacity, let us define the CD is basically capacity for, or let me use the same notation as I have used in the PPT. So this is the CM basically. CM, that is a capacity between source and destination, and it should be defined by the simply Shannon rule, that is log base to 1 plus gamma t or lambda t, and the capacity for Wire channel should be 1 plus gamma e. That's it. Where you know that the gamma d and lambda d and lambda e are already available in these two equations. Let us define the equation number here. So this is, let's say, equation number 3. This is equation number 4. This is 5, 6, 7, and 8. Let us define the equation. Now, now the next step is the actual performance measures in terms of some metrics basically. So what is the metric? So there is a number of metrics available, and but we generally interested in 3 matrices. Number 1 is outage probability. Number 2nd is average bit error rate or symbol error rate, and 3rd is the capacity. It should be actually ergodic capacity or average capacity. So these are the 3 performance measures by which we can analyze the system behavior, or we can analyze the performance of the system by analyzing the outage probability, average bit error rate, and the average capacity. So here I'm just interested in the first performance measure, that is outage probability. But this outage probability is renamed basically. This is renamed. This is renamed as the secrecy outage probability, because of the integration of physical air security aspects in the system. So the people have suggested the new term known as the secrecy outage probability. So how to calculate? So our aim is here to calculate the secrecy outage probability. So as we know, and these two are almost same basically. These two are almost same because these two are actually giving you the error performances. Okay, these two are basically defining the error performance, where the bit error rate scenario basically considering the modulation types as well, where the outage probability you are just simply checking whether the system is in outage, whether, or the meaning is whether the system is transmitting the or the transmission is basically smooth or not. So this is basically the outage probability is informing to us. Okay, so let us define the secrecy probability here. Secrecy outage probability. So this is very simple here. The secrecy outage probability defined as the probability when the secrecy capacity, let us, I'm defining the SSEC, is less than the target rate. Let us define R. This is this predefined target rate. This is very standard. Definitely, this is a standard observation of having the successful transmission. This capacity should be always, although the we need to have these two observation in the information theory, that C, the channel capacity should always be greater than the information rate, and this is the another, otherwise the system will be in outage. So this is the outage scenario. Nothing will be transmitted. So we need to check. That's why we are actually working with we are actually dealing with the worst scenarios. So we are checking our channel capacity is less than the predefined target rate. So what is the probability of having this? This we are considering, because this is definitely a true event. If C is greater than R, everything is successful. Okay, but we want to check what will happen, or what is the probability of capacity less than the target rate, basically. So we know that our secrecy capacity is basically this, which is less than R. Okay, or let me define it like this. Let me define it like this. This is the probability of maximum Cm minus Ce, comma 0 less than R. Now there may be two cases. First case is when Cm is less than Ce. Another is when Cm is greater than Ce. So if you see this particular case, we have already discussed the capacity of the eavesdropper link is much better than the capacity of the main link, which indicates that you have to compromise with the capacity, and let us define, if I'm defining here the P out as the secrecy capacity symbol, so it will be equal to 1. Whereas this is basically our case of interest. What will happen when Cm is greater than Ce? So this is because with the help of this particular case, we need to achieve the perfect secrecy scenario. So let us consider this case, because here we have compromised with our outage probability under this particular situation, which is equal to 1. So let us define what will happen with this particular part. So if you define this here, so your outage probability can be simply written as the probability of Cm minus Ce is less than R. That's it. So this is our case of simplification, basically. So this is, let us assume, some equation number 9. So now I will invoke simply. So now I'll give you the steps how to simplify the problem, basically. So if you invoke each and every step here, we know that what are the probabilities. This is log base 2 1 plus gamma d, delta d, for example, or sorry, lambda d. This is log base 2 1 plus lambda e, and this is less than R. You can further simplify it in terms of log base 2 1 plus lambda d divided by lambda e by applying the logarithmic rules, and this can be written as like this. And finally, you can express like this: 1 plus lambda d 1 plus lambda e is less than 2 raised to the power of R. So this you need to simplify, actually. This particular part you need to simplify. So why we are calculating the probability? Because we are having the instantaneous channels. Okay, so we need to calculate the probability of this particular part. So the next step basically involves, so I'm further simplifying it. So the P out is the probability 1 plus PS divided by N naught HM square divided by 1 plus PS divided by N naught HE of mod square less than 2 raised to the power of R. So just to avoid the repetition of this PS N naught and 2 raised to the power of R every time, just I'm assuming few notations here. So PS by N naught I'm assuming with some rho. This is, and this 2 raised to the power of R I'm assuming with some eta. Okay, so that I can avoid the repetition, the quick repetitions of writing this PS by N naught and 2 raised to the power of R. So I can simply write like this: P out is equal to probability of 1 plus rho HM of square divided by 1 plus of rho HE of mod square less than 2 raised to the power of R. Okay, so now we need to simplify this. But before simplifying this, there is a problem here. What is the problem? If you see here, the P outage is basically the probability of 1 plus rho HM square divided by 1 plus rho HE mod square less than eta. I'm having the HM square and HE square in picture, basically. Whereas I only know the information about HM and HE, the probability density function and the cumulative density function of HM and HE is known to us, but HM square and HE square is not available with us. So our first task should be to calculate the HME square and HE square, probability density function and the cumulative distribution function. So here I'm not going into the detail of the calculation of these two. So I'm quickly writing here the probability density function and the cumulative distribution function of these two. So if you write the HI square here, so the PDF will be 2 divided by omega I1, omega I2, K naught, and now it will be 2 root times of x divided by omega I1, omega I2, and this will be 2 divided, it will be 1 minus 2 divided by omega I1, omega I2 of root x K1 2 divided by of x omega I1 omega I2, where I belongs to both M and E. So by putting M, you can calculate the PDF and CDF for main channel, and by putting E, you can calculate the PDF and CDF for eavesdropper channel. Okay, so now we will use these statistics in this particular equation. Now our aim is to simplify it. So I'll do some simplification here. If you simplify it by taking this to the right hand side and manipulating, so I can write like this: 1 minus probability, and after some manipulation, these are the simple algebraic manipulation you can perform. HE square is basically less than HM of square eta minus eta divided by of eta times of rho. So this is our main interest basically. So here let us consider this, because one is constant and we need to only calculate this particular part. So I'm assuming, let us say this is I. So I here can be expressed in terms of the integral form, because whenever you are calculating the probability of any random quantity, it can easily be simplified with the help of its equivalent representation, which is in terms of integration basically. So that is, if you simplify it, you will observe this is nothing but eta minus 1 by e rho to infinity, 0 to some y by eta minus 1 of eta rho. This is PDF of HE mod square x dx. This is 1, and another is h of m square of x, sorry, y into dy. This you can simplify. If you further observe here, you can simply express it like eta minus 1 by rho to infinity. Now this is 0 to some value, that is, and inside this integration, that is the PDF. So you can simply write this is nothing but the CDF, having the argument y by eta minus 1 by eta rho FHM of mod square y into dy. So this is our main interest basically. This is our main interest, and this is simply the integration here. So now I'm not further going into the detail of each and every steps. I'm giving you the specific details how to simplify it. What you need to do, you just take the PDF, because what we require here, we need to have the CDF of HE square, which you can take from this. You need to take the PDF of HM square, which you can take from this particular part. Okay, then you can express it. So I'm giving you, just by invoking, I'm giving you how the integral will look like, and then quickly give you the steps. So the I will be look like this: eta minus 1 by rho to infinity, 2 by of omega m1 omega m2 to omega 1. Okay, and the another one is this is k naught 2 times of y divided by omega m1 omega m2 dy minus 4 times of omega E1, omega E2, eta minus 1 to infinity this root of y by eta, okay, y by eta minus 1 by eta rho, and here it is also one more term is here, omega m1 omega m2 minus sign, and it is k naught to y by omega m1 omega m2, and it is k1 2 by root of omega e1 omega e2, and finally this is the argument here. Now these two integrals you need to simplify. This is the first integral and this is the another integral. So let us assume this is the I1 integral and this is the I2 integral, for example. So I'm just giving the steps how to simplify this. So because these are some standard integrations, and it is very difficult to, it will take huge time to simplify these. If you go one by one and just first what you need to do first, you will simplify the Bessel function in some sort of representation, and then you will integrate it. So you will try to basically represent the Bessel functions and other function, very simple functions which are easy to integrate. But it is again a huge task. So there are a few direct expressions, few direct integrals are available for these types of situations. Okay, so if you see this equation I1, it is some value to infinity. So what I'll do to simplify I1, I'll first apply this logic. 0 to infinity, for example, there is some function fx is equal to alpha raised to the power 0 to alpha f of x dx plus alpha to infinity sum fx of dx. I'll use this fact first because I need to simplify this part. So how to simplify? This is always be 1 because any PDF under the curve will be 1, and for this means this particular information when available inside from 0 to alpha, there is a direct formula available. So I'm giving you the name of the book. The book name is basically the table of integrals. Table of integral series, like, so there is a formula available. The number is 6.561.16 and 6.561.18. So if you use these two formulas, you will able to find your I1 very easily. But first you need to apply this particular fact. So this is up to you how to apply this particular fact. So you can simplify it. Now if you want to simplify I2, here what is happening? There is a limit from some finite values to infinity, and there is a two Bessel functions, and the order of the Bessel function is different. It is of 0 order, it is of first order, and here there is a shifted argument y minus some quantity. There is no shifted argument although, but this is little tricky here. Okay, so you need to simplify it first. So what are the steps here? So what you need to do first, apply the change of variable. So you need to apply these two change of variables. This is the first change of variable, and another is this change of variable. Some, let's say, so these two change of variable or the transformation of variables you need to apply. Okay, once you apply these two change of variables into the equation, again your equation is very difficult to obtain. Okay, so you will see your integral is very difficult to process. So we need to further simplify it. So the next what we will apply, we'll apply this transformation, because Bessel functions are definitely very difficult to deal. So there is another function which is known as a major G function, which can easily be implemented. Okay, so this is the representation. This is the equivalent representation, means the Bessel function can be represented in terms of the major G function. This is the some special function basically, but it can easily be evaluated. This is the special function, major G function. Okay, and then you need to apply. There is another formula which you need to go to the. You can obtain this particular formula, but for which you have to apply. You have to go to the. There is a website. There is a functions.wolfram.com. The formula number I'll give you. This is 34.21.0082.01. So once you apply these steps, you can get the I2. You can calculate the I2. So what just first apply this change of variable, then after this change of variable, then after whatever the integral you will get, apply the change, apply the equivalent form of the Bessel function in terms of the major G function, then apply this formula to simplify the integral and do some manipulations. You will get the I2. So I'm just writing the final expression here, what you will get the outage probability. So the final outage probability expression will be look like this. This is the rho minus 1 divided by rho omega m1 omega m2 k1 to eta minus 1 divided by rho m2 plus omega m1 omega m2 divided by omega e1 omega e2, and now there is a infinite summation. So I'm writing first here. This is k, and finally this is multiplied with this Bessel function. Sorry, this major G function. This is minus half, k minus half, k minus half, and k minus half. So this is our final expression of the outage probability, from which we can observe few things. The first thing is Bessel function in the first expression, and we know the behavior of the Bessel function. If you see the Bessel function, it is just like a exponentially decaying function kind of thing. If you see the behavior, okay. So by seeing this SNR, that is signal to noise ratio here, which is I have mentioned with rho, that is PS by N naught, you can predict what is the behavior of Bessel function. So means by increasing the rho, what will be my K1 value, and what by decreasing the rho, what will be my K1. According also, if you see the P outage is basically a function of 1 by rho, which means here it is inversely proportional function. Also, you can get the idea what is the relation between the outage probability and the target rate or the threshold, basically eta, because eta we have assumed 2 raised to the power of r. 2 raised to the power of r. Just a minute. So this we are actually getting the 2 raised to the power of, that is a threshold. So we can also get the relation between these two. So the idea is, so once we are able to calculate the performance in terms of the outage probability, various things we can directly check from this expression, because these Bessel functions, the major G function, their behavior is available to us. Their equivalent representation in terms of the summation, in terms of the integrations are available. So by observing the relation between the outage and the eta, outage and variances, outage and SNR, you can easily predict what is the behavior of the system basically. So, and this simple is very, this if you see this expression is very simple, it can easily be evaluated, it can easily be implemented. Okay, the only thing is you just need to check the infinite series expansion, because if it is not converging, then your answer will be, you won't get any answer. Okay, so it is mandatory to check whether your summation, that is an infinite series expansion, is basically converging or not. So here we have already checked for this particular case, it is converging. It is giving you it is basically converging only for 0 value. That is just keeping the value of k is equal to 0, you will get the answer. Okay, because for other values of k, major G function is vanished basically, because major G function is having certain conditions of its own argument. It should be true under all conditions basically. If it is not true under all conditions, for the rest of the conditions we can ignore for that particular summation, and we will check only for that value which is it for which it is converging. The whole scenario is converging basically. So how to check basically? So quickly I am giving you the which I have already coded here. So this expression, are you able to see the this Mathematica slide?
Not yet, sir.
Oh, just give me. I think it's okay now.
Yes, sir.
Okay, so the expression which we have derived here, this expression, this whole expression we have first implemented in Mathematica in this way, one by one. Okay, so we have mentioned the rho h rho, that is rho 10 raised to the power of rho h dB, that is because SNR should be in dB, but because all the rest of the quantities like threshold, these quantities are in linear, these are the linear values, so we need to first convert our SNR in the SNR and dB in a linear scale basically. So also the omegas, all omegas like omega 1 m, m1, omega m2, all are in dB, so we have further converted in the linear scale. So we have defined here according this is the initialization of our parameters first. Then we have wrote the whole program here, which is basically let me show you this screen here. Yeah, so if you can observe these two simultaneously, now it is okay, I think. So if you can observe here, this particular expression which is mentioned here, it is exactly expressed here in the Mathematica, basically in the Mathematica software. And now you can observe here one by one, because major G is also available in the Mathematica, Bessel function is available in the Mathematica, square root is available in the Mathematica. Okay, so we have defined each and every quantity here, and this particular expression, all terms we have wrote here, and then we have checked like k is equal to 0 to 0. So if you, I have mentioned initially it should be 0 to infinity. I can write like infinity, but you won't get any answer for this. Okay, if I'll run this particular expression here, so it will be in some, let's say, keep on continuously, it is running continuously basically, you won't get anything. Okay, so I have checked it for k is equal to 0 only. Okay, so we obtain this particular value, and this is specifically for when my main link variances are much better than the wiretap link variances, that is 10 dB, and here it is a 5 dB of value. So if you let me close it and open it again, then you will get the, just a moment. Now it is available, it is visible, I think.
Yes, sir.
Yeah, so if you run it for k is equal to 0 only, it will be converged, and you will get the answer. Now see, it is, the program is already run, and you have got the answer, this for minus 10 to 30 dB, and each of a 5 dB of difference basically. But how to verify it? So to verify it further, we can have the MATLAB code, basically MATLAB program. So I have also mentioned here, let's say, let me share the, yeah, this is the simulation of Yeah, this is the simulation code of this particular scenario, this particular case study. So what we have done, we have first initialized our number of trials, then the
Sir, can you
target.
zoom it a bit?
What happened?
Can you zoom it? It's not visible.
Okay, let me check. Okay. Now is it visible?
Better than before.
Okay, let me check. Give me a minute.
You can change the font size.
It is actually in MATLAB, na?
Yes, sir, you can change it.
Just give me a minute. Okay, I have mentioned here. Let me, so that it will be much better. Give me another.
Sunil, can you just try this control plus? Maybe it will work. Control plus.
Let me check, sir.
Please try control plus.
No, it's I think not working. But I think
click outside the window, then press control plus.
Just give me a moment, sir. I think this will be much better. I think I have pasted in my this word. I think it is okay.
Okay. There's
Yes,
fine. Go ahead.
So this is the same which I have copied from the MATLAB. So this first I have initialized the number of trials, that is I have used here 10 raised to the power 5 number of trials, independent trials basically, and this is basically the Monte Carlo simulation to validate our results. And I have assumed the rate, the target rate is 1, so accordingly I can calculate the threshold, that is 2 raised to the power of r. This is the initialization for loop, or the basically the increment of values. Then you can define your SNR dB from -10 to 30 dB for each of 5 dB difference. Then you can initialize these parameters, because we want to calculate for PT, that is the our SNR, or the power basically, and not the noise power I have assumed to be 1. So the PT can be considered as the SNR, that is 10 raised to the power of SNR dB by 10. And the rest other values you can just exactly have initialize as we have done for the Mathematica. As you can observe here, omega m1 m2 are 10 dB and the omega e1 e2 are the 5 dB. Then the another task is to generate the double Rayleigh fading channel basically. So we can observe here, if you can see this particular expression which we have derived here, the HM square. So HM square is basically a HM1 square and multiply by the HM2 square, means HM1 square. So when we are assuming the HM is the Rayleigh distributed, so HM1 square is basically the exponentially distributed, and it is a product of 2 exponentially distributed variables, basically random variables. So by having this fact by knowing this particular fact, what we have done, we have generated our HM, that is the double Rayleigh fading for omega 1. Omega 1 here is basically the variance for the variance of the exponentially random variable here, and the multiplied by the another exponential random variable, that is xp_rand. Accordingly, we have generated for xe2, the wiretap channel HE, that is a double Rayleigh fading channel. Then we use x1. I have just assumed these variables x1 and x2, that is 1 plus pt multiply hm. So you can see this expression if you can observe here, cm, because this is the capacity. So let me share here like this: 1 plus ps by n naught hm square, because n naught I have assumed to be 1 for a mean time. So you can just simply take 1 plus pt or ps. It is just a matter of notation, hm square. And also you can define the 1 plus ps of he square, which I have mentioned here. So this you can define. So specifically I have not mentioned HME square, because HME square is itself, I have mentioned experience multiply experience. So it is basically the HME square. Okay. Then divide by these two, x1 divided by x2, which I have mentioned here. This divided by this basically, and should be less than some threshold, that is 2 raised to the power of r. So you can calculate the if condition. If it is less than this, so your outage will be incremented by 1, which you have already initialized by out is equal to 0. And accordingly, you can do it for number of iterations, that is 10 raised to the power 5. And finally, you can get your result. So this is the simple code for this particular simple problem although. And then what we need to do, what basically I generally do. So this is the MATLAB simulation code. I'll calculate the values from Mathematica for a particular set of parameters. I paste it here, and if I'll run this program, so what should be my output? My output should be my analytical result, which I have calculated with the mathematical expression via MATLAB software, should be matched with the simulation results, which I have obtained via the MATLAB software. So if I'll run this, so you will get it's taking, because it's a 10 raised to the power 5, so it will take some time, but I'll have the final result. I'll share this with you quickly. I'll also share this. Yeah, now this result I have just plotted for various combinations, various set of parameters. So if you observe here, the simulation result and analytical results both are matched for all set of parameters for different omega m1, omega m2, omega e, omega e2. For a meantime, I have assumed the omega m1, omega m2 all are equal. And if you want to calculate for a different values of omega m1, omega m2, you can calculate. So you can observe here that when the strength of main link is greater than the strength of wiretap link, that is 10 dB is greater than the 5 dB definitely. So you are getting better outage probability, But at the same time, as the strength of the I think here it is slight mistake. You can correct it. This is basically 15 dB for omega E1 basically. This particular copper, when the upper one, this is omega E1, omega E2 is 15 dB, and omega M1, omega M2 is a 10 dB. Means here the strength of the eavesdropper link is much better than the legitimate link. So the idea is very simple. Whenever the outage, whenever this link of or the strength of the wiretap link is better than the strength of the mail link, you will get the poor performance, or otherwise you will get the good outage performance here. So okay, the result, we have got the result here. Now you can observe here. You can see. I think result is visible. This result.
Yes, sir.
Now you can observe. So this simulation result, this bold line basically for analytical result, and these square are basically the simulation points. So they are exactly matching from -10 dB to 30 dB, which validate the correctness of our mathematical expression which we have obtained. So this is how we generally model our systems, and although we don't have enough time to elaborate here, but by just observing these expression, basically this particular expression, final expression, we can get these several remarks directly. Okay, rather let's say if you know the major G function, behavior of the major G function, we can directly say like this: by increasing the threshold, what will be my outage, or my outage, and which even you can also calculate the dominating factors or dominating values or dominating functions among these different parameters available here. So various things you can directly conclude from these expressions, but we need to validate it, and so we can simply calculate this particular expression in the Mathematica, and then it will be verified by the MATLAB simulations. That is a Monte Carlo simulations basically. So this is how we generally model our performance of a particular system. But here particularly we have seen for the physical air security performance for vehicular to vehicular communication. So I think this is all about from my side. Yeah. So if you have any question, any doubt related to this, so we can discuss it.
Any questions from participants?
This is
If there are
Yes.
no questions, then I can thank Dr. Sunil Yadav for giving such a beautiful talk on this physical air security and in B2B communication. And all of you are having another opportunity to interact with him tomorrow also, where he would be delivering a talk on reconfigurable intelligent surface enabled wireless communication. So if there are some questions in your mind about this physical air security, you can even raise the questions tomorrow also, at the beginning itself.
Yeah, or otherwise I'm mentioning my email ID here. If you have any question later on, you can just mail to me. I'll reply back.
We will be very happy to answer your queries.
Yeah. So it's my email ID. You can email me for any query related to this particular talk, so we can discuss it separately.
So, thank you, Dr. Cyril, once again.
Yeah, thank you, sir. Thank you so much.
So, now I think all of us can leave. And one more thing to the participants, we have provided the link for the video lectures on your email as well as on your WhatsApp group. So please check it. And tomorrow morning, they are going to be, we are meeting again at 9:30. And the talk will be, first talk will be delivered by Professor Vimal Bhatia from IIT Indore. And in the first talk, he will be discussing about IoT and its implementation issues. Then he will also deliver the second talk, that is on visible light communications. And at 2:30 tomorrow again, we are going to have another opportunity to interact with Dr. Sunil. So till then, till tomorrow morning, from my side. Thanks, Dr. Sunil, once again. Bye.
Thank you, sir. Thank you so much, sir.